What if everything we thought we knew about the universe was a mistake? Not just a little off, but completely, terrifyingly wrong. We've been taught that science moves us forward, that we discover, we confirm, and we build. But what if some of our most celebrated discoveries were never fully understood in the first place? What if the things we thought were settled, how galaxies form, what stars are made of, what space is actually doing, are just placeholders for deeper mysteries we haven't cracked yet? The night sky looks calm, peaceful, predictable, but it's not. It's full of contradictions. Stars behaving like they shouldn't, galaxies forming way too fast, signals that arrive from nowhere and disappear without explanation. And buried under all of it are questions we don't like asking, because the answers might not make sense. The more we learn, the stranger it gets. The Big Bang? Still debated. Dark matter? Still invisible. And some discoveries, the ones too weird to fit neatly into a theory, get buried, dismissed, or quietly ignored. So here's the real question. Have we been forcing the universe to fit our story? Or is the universe trying to tell us one we're too afraid to hear? This isn't about conspiracy. It's not science fiction. It's about what happens when evidence shows up that nobody wants to believe, because it rewrites everything. And once you see it, you can't unsee it. The universe doesn't just surprise us, it messes with our heads. At first glance, space feels calm, peaceful. The stars twinkle, the planets orbit, and everything seems to follow some kind of beautiful, mathematical rhythm. But that's just the surface. Behind that calm sky is chaos, confusion, contradictions, and discoveries that don't make any sense. For centuries, astronomers have looked up expecting to confirm what they already believed, and instead found something that rewrote everything, not once, but again and again. That's what makes space so fascinating. It's not just full of answers, it's packed with mysteries that challenge our most basic ideas. Like, what if the universe isn't as old as we thought? Or what if it's older than it should be? What if galaxies are forming too early, too fast, or somehow not forming the way we expected at all? Every time scientists think they've nailed down how the universe works, something shows up that doesn't fit. A galaxy that's too massive, a star that's too old, a signal that comes from nowhere and disappears just as quickly. Sometimes it's a telescope glitch, sometimes it's human error, but other times, it's something real. Something that doesn't go away, no matter how many times it's tested. And those are the moments that flip the entire field of astronomy on its head. That's the funny thing about space. The more we learn, the more we realize how little we understand. We thought Earth was the center of the universe. Wrong. We thought the Milky Way was the entire cosmos. Also wrong. We thought space was still and timeless. But now we know it's expanding, and maybe even speeding up. And dark matter? We still don't know what it is. We only know we need it, or the math falls apart. These aren't just weird side notes. They're turning points. Moments where science itself had to pause and admit, okay, this changes everything. They don't happen every day, but when they do, they leave a permanent mark, not just in textbooks, but in how we think about reality. This isn't a story full of clean conclusions and neat little facts. It's a story about the uncomfortable discoveries, the ones that leave scientists confused, the ones that force theories to evolve, the ones that remind us that even in the age of powerful telescopes and complex simulations, the universe still has the final say. So, if you came here for answers, you might leave with more questions. And that's exactly the point. The biggest problem in science isn't what we know, it's what we think we know. Because sometimes the most trusted ideas fall apart, not with a bang, but with a whisper, a small flash, a sudden wobble, a strange reading that no one can explain. And once it's noticed, everything changes. But that brings up a bigger question. How do we even know what's real? How do you trust your understanding of the universe when the universe refuses to sit still? What if the rules we've built everything on are just temporary? What if gravity doesn't work the same way everywhere? What if time isn't as consistent as we think? How can a star be older than the universe? How can entire galaxies exist without the thing we say holds them together? What do you do when one discovery quietly unravels 100 others? Why do some galaxies grow up faster than they should? How do we explain light that comes from nowhere, or matter that we've never seen but swear must exist? What happens when you point the most powerful telescope ever built into space and see things that shouldn't be there at all? What if the next mistake isn't a mistake at all, but a message from the cosmos that we're missing something huge? And the real question is, are we even ready to find out? Because the more we look, the stranger it gets, and the universe isn't slowing down for us to catch up. Let's start at the beginning. When the Earth stopped being the center of everything, for most of human history, Earth wasn't just a planet. It was the planet, the center of everything, the cosmic stage around which the sun, the moon, the stars, and even the gods revolved. That wasn't just a belief, it was reality, unquestioned, obvious. You looked up and everything moved across the sky. The Earth, it didn't move. It felt solid, immovable. The ground beneath our feet couldn't possibly be racing through space. It sat at the center, still stable, special. This idea was so deeply rooted in human thinking that it didn't even feel like science. It was philosophy, culture, religion, a truth that shaped how people saw their place in the universe. From ancient Babylon to Aristotle's Greece, and later through Roman scholars and Christian theologians, the Earth-centered or geocentric model wasn't just dominant, it was everything. According to this model, the heavens were a set of perfect crystal spheres rotating around Earth in fixed layers. The stars were embedded in one, the planets were in others, the moon, the sun, each circling us like a cosmic ballet, perfectly tuned, eternal. This system didn't just come from superstition, it was logical, for the time. It explained the motion of the stars, it made sense of the rising and setting sun, and it was backed by the most respected minds of the ancient world, thinkers like Ptolemy, who refined the model into a complex system of circular orbits within orbits, called epicycles to account for strange motions like Mars occasionally moving backwards across the sky. It was elegant in its own way, and it held up for centuries. But even the most carefully polished illusions eventually crack. Enter Nicholas Copernicus, a man who didn't set out to challenge the world, but ended up doing exactly that. Born in 1473 in the Kingdom of Poland, Copernicus wasn't a loud revolutionary. He was a scholar, a church canon, a man of quiet intellect. He studied law, mathematics, astronomy, and medicine. And over time, he began to notice that the traditional models didn't quite work. The math, no matter how clever, was becoming too complicated. Epicycles piled on epicycles. The system started to look less like divine perfection and more like a desperate attempt to make the sky behave. So Copernicus asked a simple question. What if we had it backwards? What if the sun was at the center and the earth moved? It sounds simple now, but back then, it was almost unthinkable. To suggest that Earth wasn't the center of everything was to cut humanity down to size. And worse, it flew in the face of religious teachings, which placed humankind at the heart of creation. But Copernicus followed the math, and the more he looked, the more things made sense. Planets that looped backwards in the sky, they weren't really reversing. It only looked that way because Earth itself was moving. The odd brightness of some planets at different times, that too could be explained by their orbits around the sun, not Earth. So he began to write, quietly, carefully. Over decades, he worked on a manuscript that would become De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. It proposed a heliocentric model, one where the sun stood still, and the Earth, along with the other planets, orbited around it. Earth wasn't fixed either. It spun on its axis daily. The heavens weren't circling us, We were turning through them. But Copernicus didn't publish it right away. He hesitated. He knew this was dangerous territory. He revised it, tweaked it, hid it, for more than 30 years. Only near the end of his life, in 1543, did he allow it to be printed. According to legend, he saw the first copy on his deathbed, and then he died. At first, the reaction was muted. Some scholars read it, a few even liked it, for its mathematical neatness, not because they thought it described the real world. To most, it was just a curiosity, a hypothesis, nothing more. After all, Earth didn't feel like it was moving. There was no wind from motion, no slingshot effect. The church didn't crack down on it immediately. They didn't need to. No one took it seriously enough, but someone did. His name was Galileo Galilei. Unlike Copernicus, Galileo was loud, charismatic, provocative. He loved attention. He also loved proof. And when he heard of a new invention from the Netherlands, a device that used lenses to magnify distant objects, he saw an opportunity. He didn't invent the telescope, but he made it better, stronger, powerful enough to peer into the sky like never before. And what he saw changed everything. He looked at the moon and saw mountains, craters, shadows, not the perfect, smooth sphere described by ancient texts, but a scarred, rocky world. He pointed it at Jupiter and saw something stunning. Tiny stars moving around it, 4 of them, moons, orbiting not the Earth, but another planet. If Jupiter could have moons, why couldn't Earth move too? Then he turned the telescope to Venus. And this was the real moment. Venus, according to the geocentric model, should only show crescent phases. But Galileo saw something else. Phases that matched what you'd see if Venus orbited the sun. Like our moon, it went from crescent to half to full, only possible in a sun-centered system. Galileo had done what Copernicus couldn't. He gave the heliocentric model teeth, evidence, proof. But he didn't stop there. He wrote about it, passionately. He published his findings in Sidereus Nuncius, the Starry Messenger, in 1610. He didn't write in Latin, the language of scholars. He used Italian, the language of the people. He wanted everyone to understand what he'd seen. The heavens weren't perfect, the earth wasn't central, and observation, not tradition, should guide science. To the scientific world, it was electric. To the church, it was a problem. The Catholic Church had long balanced faith and science. But Galileo's work, bold, public, loud, was threatening that balance. He wasn't just suggesting a new theory, he was telling people that the old one was wrong, and he was doing it in front of crowds. In 1616, the Church officially declared heliocentrism formally heretical. Galileo was warned, told to stop, and for a while he did. He backed off, kept quiet, but he couldn't stay silent forever. In 1632, he published a new book, Dialogue Concerning the Two Chief World Systems. It was written as a conversation between 3 fictional characters, one supporting the Copernican model, one defending the Ptolemaic, and one neutral. But it was obvious where his loyalties lay. Worse, the character defending geocentrism came off as kind of an idiot. Many believed he was mocking the Pope himself. That was the last straw. Galileo was summoned to Rome, put on trial for heresy, forced to recant. Under pressure, he denied that Earth moved. He swore he no longer believed it. Legend says as he left the court, he muttered, "Eppur si muove," and yet it moves. Galileo spent the rest of his life under house arrest. He wasn't allowed to teach or publish or speak publicly on the subject again. But the damage was done. The idea was out there. The telescope had opened the sky, and the old world, with Earth at its center, was starting to fade. The shift from geocentrism to heliocentrism wasn't just about where Earth sat in the solar system. It was about where we sat in the universe. Before, we were the center of creation. After, we were just a small planet orbiting an ordinary star in a vast galaxy. It was a demotion, Not just scientifically, but philosophically, spiritually, and it terrified people. But not everyone resisted. New thinkers emerged, Kepler, Newton, and others, who took the heliocentric model and built on it. They found laws of planetary motion, gravity, mechanics. Suddenly the universe didn't just look different. It made sense. It could be measured, predicted, explained. The church eventually lifted its ban on Galileo's books, but that came centuries later. By then the world had changed, not because of force, not because of rebellion, but because of one quiet idea, that the earth isn't the center of everything. And that idea made the universe bigger than anyone had ever imagined. The great debate: is the universe bigger than the Milky Way? Let's rewind back to a time when the entire universe, as far as most scientists were concerned, was just one galaxy, our own, the Milky Way, a vast star-filled island suspended in darkness, and supposedly the only one that existed. It sounds strange now, knowing what we know today, but back in the early 20th century, even top astronomers genuinely believed that everything, the stars, the gas clouds, the fuzzy little blotches seen through telescopes, was part of a single cosmic structure. Earth wasn't at the center anymore, but maybe our galaxy was. Maybe this was it, the whole show. But not everyone agreed. By 1920, that debate had reached a boiling point. Scientists had been looking through telescopes for centuries, and they kept spotting strange, blurry patches of light. These weren't stars. They didn't shine like stars. They didn't behave like stars, and they didn't follow the same paths. They were different. Some looked spiral-shaped. Some had structure, but no one could agree on what they actually were. Were these nebulae just clouds of gas floating inside the Milky Way? Were they clusters of stars being born? Or were they something bigger, something completely outside our galaxy? That question became the heart of one of the most important and heated scientific disputes of the 20th century. A clash that wasn't just about data, it was about perspective, about our place in the universe, about whether we were living inside a small, cozy galaxy or floating in an ocean of billions more. This moment, this battle of ideas, would go down in history as the Great Debate. It was April 26, 1920. The location: the Smithsonian Institution in Washington, D.C. The two scientists at the center of it all were Harlow Shapley and Heber Curtis, both brilliant, both respected, and both completely convinced that they were right. Shapley was a bold thinker. He had spent years studying globular clusters, those tight, spherical groups of stars that hover on the outskirts of the Milky Way. By analyzing how far away these clusters were and how they were arranged, Shapley came to a startling conclusion. The Milky Way wasn't small, it was enormous, much bigger than anyone had thought. And most shocking of all, according to his data, the sun wasn't even close to the center. That was already a big deal, moving humanity even further away from the metaphorical spotlight. But Shapley went further. He believed that all those spiral nebulae, those swirling, mysterious blobs, were inside the Milky Way, not beyond it. They were just parts of our own galaxy, maybe forming stars or acting as weird cosmic leftovers. The idea of other galaxies, to him, it just wasn't necessary. We didn't need them to explain what we were seeing, so why make the universe bigger than it had to be? But then there was Curtis. He wasn't so convinced by Shapley's giant Milky Way model. In fact, he thought it was way too big. He believed the galaxy was smaller, and more importantly, he didn't think it was the only one. Curtis argued that those spiral nebulae weren't inside the Milky Way at all. He thought they were island universes, his term for what we now call galaxies. Separate systems, far beyond the reach of our own, each with their own stars, gas, dust, and mysteries. It wasn't just a theoretical disagreement. It was a complete difference in how they looked at the sky. Where Shapley saw one enormous galaxy filled with everything, Curtis saw a more modest Milky Way, floating in a sea of distant neighbors. During the debate, both men laid out their evidence. Shapley leaned on his analysis of variable stars and the distances to globular clusters. Curtis pointed to photographic images of spiral nebulae showing signs of rotation and structure, hints that they were more than just gas clouds. He also noted that novae, sudden explosions of stars, had been seen in these spirals, and the brightness of those novae suggested the spirals were incredibly far away. They debated respectfully but firmly in front of an audience of astronomers and scholars. There were no fireworks, no mic drops, just calculations, arguments, and quiet tension. And in the end, no clear winner. There was no decisive vote, no official ruling. People walked away with the same uncertainties they came in with. But what made the great debate so legendary isn't that it solved everything. It's that it set the stage for what came next. Because just a few years later, someone would come along and settle the argument once and for all. His name was Edwin Hubble. At the time, Hubble was working at Mount Wilson Observatory in California. There, astronomers had access to the Hooker telescope, then the most powerful telescope in the world. And Hubble knew exactly what he wanted to point it at: the Andromeda Nebula. This was one of the most famous and mysterious spiral blobs in the sky. It was big, bright, beautiful, and confusing. Was it part of our galaxy, as Shapley believed? Or was it a separate galaxy entirely, as Curtis had suggested? To find out, Hubble used a clever trick. He searched for a special kind of star inside Andromeda, Cepheid variables. These stars pulse in a regular rhythm, and their pulsation period is directly linked to how bright they actually are. So by measuring how bright they look from Earth, you can calculate how far away they are. It's like having a built-in cosmic yardstick. In 1923, Hubble found one, then another, then more. He did the math, and the result was jaw-dropping. Andromeda wasn't in the Milky Way. It was far beyond it, over 2 million light-years away, which meant it wasn't a nebula at all. It was a galaxy, a huge independent system filled with its own stars, planets, gas, dust, all orbiting around a center, just like the Milky Way. In that moment, the universe expanded beyond imagination. It wasn't just us anymore. There were others, lots of them. What Curtis had guessed was now fact. What Shapley had missed was now undeniable. And the universe was no longer a one-galaxy story. It was a vast, crowded cosmos with billions of galaxies. But there was a deeper shift too, one that went beyond telescopes or theories. This was one of those rare moments in science where a single discovery rewrites everything. Because it wasn't just about how many galaxies there were. It was about how small we suddenly felt. We weren't living in a cosmic mansion. We were living in one house, on one street, in a city of unimaginable scale. It was humbling, awe-inspiring, and kind of terrifying. And yet, it opened the door to everything that followed. Hubble didn't stop there. After proving that other galaxies existed, he began measuring how fast they were moving. He found that the more distant a galaxy was, the faster it appeared to be racing away from us. This would lead to an even bigger idea: the expanding universe. And later, the Big Bang. But it all started with the Great Debate, a conversation between two men who dared to ask, what if we're wrong? That debate didn't end with applause or agreement, but it ended with a telescope, a star that blinked, and a realization that changed human history. The universe was bigger, much, much bigger, and we were just getting started. The expanding universe. When Edwin Hubble began studying the night sky in the 1920s, he probably didn't expect to rewrite the entire story of the universe. He was just doing what astronomers do: observing, measuring, cataloging. But the deeper he looked into space, the stranger things became. He wasn't just seeing stars and galaxies. He was seeing a pattern, a subtle shift in the color of light that would lead to one of the most shocking realizations in the history of science. Here's what happened. Hubble had access to the Hooker telescope at Mount Wilson Observatory in California. which at the time was the most powerful telescope in the world. It gave him the ability to observe distant galaxies in more detail than anyone ever had. He started by looking at their spectra. The light spread out like a rainbow using a prism, and he noticed something odd. The light from these galaxies wasn't where it should be. When light from a galaxy passes through a prism or spectroscope, it creates lines, signatures of elements like hydrogen or helium. But those lines were shifted. Specifically, they were shifted toward the red end of the spectrum. That might sound minor, but it was a huge deal. Because in physics, this kind of shift, called redshift, means something is moving away from you. It's like the Doppler effect you hear when a siren passes you on the street. The pitch is higher as it approaches and drops lower as it moves away. Light does the same thing. When a galaxy is moving away, its light gets stretched out, and stretched light appears redder. Now, a few redshifts wouldn't be surprising. Maybe a handful of galaxies were drifting away, but Hubble found that all the galaxies he observed, every single one, were redshifted. And more than that, the farther away a galaxy was, the more its light was redshifted. That could only mean one thing. Galaxies weren't just drifting, they were speeding away from us. The entire universe was expanding. At first that sounds wild. How can the universe expand? Expand into what? And where is the center? But the idea wasn't actually brand new. A few years earlier, in 1922, a Russian physicist named Alexander Friedmann had taken Einstein's equations of general relativity and found that they allowed for something strange, a dynamic universe, one that could grow or shrink over time. Einstein had dismissed the idea. He preferred a steady, unchanging cosmos, so much so that he added something artificial to his equations, a cosmological constant, to force the universe to stay still. Without it, the math pointed toward movement, expansion. But Einstein wasn't ready to accept that. Then came Hubble, with hard evidence. When he published his results in 1929, it was undeniable. The farther a galaxy is, the faster it's moving away from us. That meant the space between galaxies was getting bigger. The universe itself was growing, not like an explosion pushing matter into empty space, but like space itself stretching out, carrying galaxies with it. Imagine blowing up a balloon. If you draw dots on the surface and start inflating it, the dots move away from each other, not because they're flying through the air, but because the surface itself is expanding. That's what the universe is doing. Every point in space is getting farther from every other point, and from any one galaxy's perspective, it looks like everything else is moving away. Now here's where it gets really interesting. If space is expanding now, that means in the past, it was smaller, and if you rewind time far enough, you eventually reach a moment when everything, every star, every planet, every atom, was packed into an unimaginably hot, dense state, a beginning. That idea became the foundation of what we now call the Big Bang Theory. But at the time, it was hard to swallow. The idea that the universe had a beginning felt too philosophical, too close to religion. Science had spent centuries pulling away from ideas like creation, and now here was evidence that the universe might have started from a single moment. Not everyone was happy about it. One of the loudest critics was a British physicist named Fred Hoyle. Hoyle believed in what's called the steady-state theory. According to that model, the universe had no beginning and no end. It had always existed, and always would. Yes, it could expand, but new matter would constantly appear to fill the gaps. That way, the universe would always look more or less the same, no matter when you looked at it. Hoyle thought the idea of a Big Bang was ridiculous. In fact, he called it that as a kind of joke during a BBC radio interview in 1949. He was mocking the concept, not naming it, but the name stuck, and ironically, it helped popularize the theory he was trying to discredit. Still, the Big Bang Theory had a big problem. It was hard to test. Hubble's redshift observations showed the universe was expanding, but they didn't prove there was a beginning. For that, scientists needed more evidence, something left over from the early universe, a kind of cosmic fingerprint, and that would come later, in the form of faint microwave radiation left behind from the early stages of the universe. But that's a story for another time. Let's stay with Hubble a little longer. His work didn't just suggest expansion, it also gave us a way to measure it. The rate at which galaxies move away from us compared to their distance became known as the Hubble constant. It tells us how fast the universe is expanding today, and that number is still debated. Different methods give slightly different values. Some say the universe is 13.8 billion years old. Others argue for a bit more or less. This ongoing disagreement, called the Hubble tension, is one of the biggest unresolved issues in cosmology right now. But back in Hubble's time, even a rough estimate was revolutionary. The implications were massive. The universe was not static. It wasn't eternal. It was alive in a sense, growing, evolving, changing. Suddenly the cosmos had a timeline, a story, a past, and maybe even a future. Some people found this thrilling, others found it disturbing. Because if the universe had a beginning, what caused it? What came before? Is there an edge? Will it keep expanding forever, or will it collapse back in on itself? These aren't just scientific questions. They're existential ones. They force us to think about time, existence, and our own place in the cosmos. Even today, the idea of an expanding universe still feels kind of unreal. We're used to things moving in space, but not space itself changing. Yet all the evidence points to it. Galaxies are racing apart. Light from the past is stretched. Space is growing between everything, and that includes us. We can't feel it, because the expansion is incredibly slow on human scales. It doesn't affect you or the solar system or even our galaxy, but over millions and billions of light years, it's undeniable. And the most fascinating part? The expansion seems to be speeding up. In the late 1990s, two separate teams of astronomers observed distant supernovae, massive exploding stars, and discovered they were dimmer than expected. That meant they were farther away than they should have been. The only explanation was that the universe's expansion was accelerating. That discovery shocked the scientific world. To explain it, scientists proposed something called dark energy, a mysterious force that seems to push space apart. We still don't know what it is. It might be an inherent property of space itself, or it might be something even weirder. But whatever it is, it dominates the universe. About 70% of the cosmos is dark energy, silently stretching space faster and faster. So now, not only is the universe expanding, it's doing it faster than ever before. It's hard to overstate how much this changed our understanding of everything. The universe is not eternal. It's not static. It had a beginning. It has a structure. It might even have an end. And all of this, from a tiny redshift in distant starlight. That's what Hubble saw. That's what the spectrum told him. A whisper from the edge of the universe saying, "You don't know me yet, but I'm bigger than you ever imagined." The cosmic microwave background. In the mid-1960s, two radio engineers working at Bell Labs in New Jersey were trying to solve what they thought was a technical problem. Their names were Arno Penzias and Robert Wilson, and their job wasn't to study the cosmos. They were working on satellite communications, trying to refine microwave antennas for clearer transmissions. But something kept getting in the way. No matter what they did, they couldn't get rid of a strange, low-level hiss, a background noise that just wouldn't go away. It wasn't from nearby cities. It wasn't the sun. It wasn't even the galaxy. They cleaned their antenna, checked the electronics, even removed some pigeons that had nested inside the horn and left droppings, what Penzias later called white dielectric material. But the hiss persisted. It came from every direction. It was constant. It was cold, and they didn't know what it was. They weren't looking for a cosmic mystery. They stumbled into one. At the same time, just a few miles away, a team of physicists at Princeton University, led by Robert Dickey, was working on a completely different problem. They were trying to detect something theoretical, something that, according to their calculations, should exist if the universe had begun in a massive explosion of energy, a Big Bang. What they were looking for was the leftover heat from that event, the radiation that, even billions of years later, should still be faintly glowing across the universe, cooled down, stretched by the expansion of space, and no longer visible as light, but still there, like the dying echo of an ancient fire. They called it the cosmic microwave background, CMB for short. Dickey and his team were designing a special instrument to search for it, but before they could even begin, they received a phone call from Bell Labs. "We think we've found something," Penzias and Wilson said. It didn't take long to connect the dots. That background noise, that wasn't interference. That was it. The signal, the very thing Dickey's team had been hoping to find, already detected by two engineers who weren't even looking for it. There's a quote attributed to Robert Dick when he heard the news. He turned to his team and said simply, "Well, boys, we've been scooped." And just like that, everything changed. To understand why this discovery was so important, why it would later win a Nobel Prize, you have to understand what the CMB actually is. Imagine the early universe, not as we know it now, with stars and galaxies, but as it was, just after the Big Bang, a hot, dense soup of particles and radiation. Back then, the universe was so compact that light couldn't travel freely. Photons, the particles of light, kept bouncing off charged particles like electrons and protons. It was like trying to see through the densest fog imaginable. But as the universe expanded, it cooled. And about 380,000 years after the Big Bang, something profound happened. Electrons and protons began to combine into neutral hydrogen atoms. And when that happened, light was finally free. It could travel without being scattered. That moment, called recombination, is when the universe became transparent, and the photons from that era began their journey outward. Those same photons are still traveling today. Stretched by the expansion of space, they've lost most of their energy. What was once searing heat has cooled to just a few degrees, above absolute zero. What was once brilliant light is now microwave radiation, but it's still out there, all around us, filling the cosmos like a quiet, invisible whisper from the dawn of time. That's the cosmic microwave background. It's not just background noise, it's a snapshot of the infant universe, the earliest image we can ever have, a fossil of light, carrying with it the memory of a universe just beginning to take shape. When Penzias and Wilson published their findings in 1965, the scientific world took notice. For decades, the debate between the Big Bang theory and the steady-state model had simmered. The steady-state theory, championed by figures like Fred Hoyle, suggested that the universe had no beginning and no end, that it had always existed more or less as it is now, with new matter continuously forming to keep it looking the same as it expands. The Big Bang theory, by contrast, said the universe had a beginning, a moment of creation, a flashpoint from which everything expanded. But it needed evidence. It needed something left over from that event, a signature that couldn't be faked. The CMB was that signature. And once it was detected, the steady-state model lost its footing. This faint background radiation was exactly what the Big Bang predicted, uniform across the sky, cold, ancient, and unmistakable. It was the smoking gun. But the story doesn't end there. As observational technology improved, scientists realized the CMB wasn't perfectly smooth. There were tiny fluctuations, minuscule differences in temperature across different regions of the sky. These variations were only a few millionths of a degree, but they were there, and they were crucial, because those little ripples, those irregularities, are what allowed structure to form in the universe. The slightly denser regions had just a little more gravity, enough to pull in more matter over time, eventually forming galaxies, stars, and everything we see today. In other words, the universe wasn't born perfectly uniform, and that imperfection, is the reason we exist. This discovery was made clearer in the early 1990s when NASA launched the COBE satellite, Cosmic Background Explorer. For the first time, we could map the CMB in detail, and it confirmed everything. The uniform glow, the tiny ripples, the pattern of the early universe written in microwave light. Later missions, WMAP in the 2000s and Planck in the 2010s, took even sharper measurements. What they found was staggering. They gave us the age of the universe, 13.8 billion years. They confirmed the geometry of space. It's flat, not curved. They measured the proportions of matter, and dark energy. They even provided evidence for an idea called inflation, the theory that in the first tiny fraction of a second after the Big Bang, the universe expanded faster than the speed of light. All of that, from a whisper of radiation, born in silence, echoing across time. Today, we look at the CMB the way a detective looks at an old photograph, not because it tells us everything, but because it captures a moment no longer accessible by any other means. It's our earliest window into reality. It doesn't just show us that the universe had a beginning. It shows us what the universe was at the beginning, a hot, seething sea of potential. No galaxies, no stars, just heat, energy, and possibility. And somehow, all of that became us. The beauty of the CMB isn't just scientific, it's deeply human. Think about it. Light that started its journey nearly 14 billion years ago has traveled across the fabric of space, dodging stars, weaving through galaxies, untouched by time, only to end up inside a metal horn antenna in New Jersey, or in a satellite orbiting Earth, or in a sensor in the Atacama Desert. It's like the universe left us a message, a kind of cosmic photograph, and all we had to do was listen carefully enough to hear it. The cosmic microwave background is not just a relic, it's a reminder that the universe is vast, that it had a beginning, and that even in its earliest moments it held the seeds of everything we know. Stars, planets, life, United States, all written in light, and all waiting until someone, two engineers perhaps, happened to tune in at just the right moment. Dark matter, the gravity. We can't see. Everything seemed to be lining up. The Big Bang had become widely accepted. We had discovered the cosmic microwave background. Galaxies were no longer just patches of light, but vast star cities. And for a moment, it felt like the universe was finally giving up its secrets. But then, it pulled a fast one. It started with a simple observation. Just some stars spinning around inside spiral galaxies. Astronomers had studied them for years, mapping their beautiful arms and watching them rotate. The idea was straightforward. Stars closer to the center would move faster, pulled tightly by the galaxy's gravity. And the stars on the edge? They'd drift more slowly, kind of like how the outer planets in our solar system orbit the sun more leisurely than the inner ones. That's what Newton's laws of motion and gravity told us should happen. But in the 1970s, something unexpected showed up. An astronomer named Vera Rubin and her colleague Kent Ford began carefully measuring how stars moved in spiral galaxies like Andromeda. They weren't just glancing at photos. They were using precise instruments to measure the speed of stars, based on how their light was shifted by motion. The results were not what anyone expected. The stars on the outer edges of the galaxy weren't slowing down. In fact, they were moving just as fast as the stars near the center. Some were even moving faster. And that made no sense. According to physics, stars that far out should be barely hanging on. The galaxy's visible mass, everything we could actually see, just didn't have enough gravitational pull to hold those fast-moving stars in orbit. They should have been flung into intergalactic space like coins off a spinning merry-go-round. But they weren't. They stayed, orbit after orbit, quietly defying everything we thought we knew about how gravity works on cosmic scales. That was the moment the universe cracked open a new mystery. Rubin's observations weren't a fluke. She checked dozens of galaxies. The pattern repeated again and again. Flat rotation curves, they called them. Speeds that stayed high, all the way out to the galaxy's edge. No matter where she looked, the same ghostly hand seemed to be at work. Something invisible was keeping these galaxies together. There was only one way to explain it. There had to be more mass out there, a lot more, but it wasn't shining, glowing, or emitting any light. We couldn't see it. We couldn't touch it. All we could do was measure what it was doing to everything else. Something was holding the galaxies together, something with gravity, but not with light. We called it dark matter, and from that moment on, everything changed. Here's the weird part. Dark matter isn't just an extra sprinkle of mass. It's not just a little fudge factor to fix the math. In most galaxies, dark matter makes up the majority of their mass, up to 80%, sometimes even more. The stuff we can actually see, stars, planets, gas, dust, that's just a thin layer on top. The visible part of a galaxy is like foam on the surface of a vast invisible ocean. That's how big this is. The more we looked, the more places we found dark matter's fingerprints. It was shaping galaxies, clusters of galaxies, even the massive web of cosmic structure that stretches across the universe. Wherever we found gravity doing more than it should, pulling harder, bending light in strange ways, distorting space, it pointed to one conclusion. There's more out there than meets the eye, a lot more. You might think, well, maybe there's just a bunch of stuff we can't see, like faint stars or rogue planets or black holes. That was the first idea scientists tried. They called it MACOs, massive compact halo objects. These were hypothetical things like dim brown dwarfs, cold gas clouds, or black holes lurking in the dark, adding to a galaxy's mass without glowing. And sure, some of those things do exist, but not nearly enough of them. They simply can't account for all the missing mass Rubin found. So the next theory was more exotic. What if dark matter isn't made of ordinary matter at all? That led to a new class of hypothetical particles, things we've never seen, but that might exist if the laws of physics allow them. One of the main contenders? WIMPs, weakly interacting massive particles. The idea is, these particles have mass, so they can produce gravity, but they barely interact with light or normal matter. They could be floating all around us right now, passing through your body, your house, the earth, without leaving a trace. Billions of them, every second. And we'd never know. To detect WIMPs, scientists have built ultra-sensitive detectors and buried them deep underground, in mines and mountains, shielded from cosmic rays and background noise. These detectors are waiting for just one dark matter particle to bump into a regular atom and leave a signal. So far, nothing, just silence. But they keep looking. Other candidates include axions, tiny ghost-like particles that could drift through the cosmos and explain some of the strange behaviors we see in galaxies. There are also ideas about sterile neutrinos, supersymmetric particles, even dark matter made of mini black holes from the early universe. Some physicists think there could be whole dark sectors with dark matter forming its own atoms, forces, and maybe even dark life. We don't know. And that's what makes it exciting. Because here's the thing. We're not just guessing in the dark. We're measuring. Constantly. And the evidence keeps piling up. One of the clearest signs of dark matter comes from gravitational lensing. That's when light from a distant galaxy gets bent as it passes near a massive object, like another galaxy or a cluster of galaxies. This effect is predicted by Einstein's theory of general relativity, and it lets us see mass, even when that mass is invisible. When astronomers look at these lenses, they find more bending than the visible matter can account for. It's like seeing a shadow without a body. The gravity is there, but the mass we can see isn't enough. Then there's the cosmic microwave background, the leftover glow of the Big Bang. Tiny fluctuations in this ancient light tell us how matter was distributed in the early universe. And guess what? Those patterns only make sense if there was dark matter there, shaping the early cosmos before galaxies even formed. In other words, the story of the universe doesn't work without it. Still, not everyone agrees. Some scientists have proposed that maybe we don't need dark matter. Maybe gravity just works differently at large scales. These are known as modified gravity theories, like MOND, short for modified Newtonian dynamics. MOND tries to tweak the laws of gravity so that galaxies rotate the way we see them, without needing invisible matter. It's a bold idea, and in some cases, MOND fits the data, but it struggles in others, especially when you look at galaxy clusters, lensing effects, or the cosmic microwave background. Dark matter still explains more even if we don't know what it is. That's the frustrating part, and the beautiful part. Because science isn't just about finding answers, it's about finding better questions. Right now, the search for dark matter is one of the biggest open questions in all of physics. It's the missing puzzle piece in our picture of the universe. We can see what it does. We can map it, chart it, model it. We know where it has to be, but we can't name it. We can't touch it. And maybe we're not supposed to. Not yet. Maybe it's the universe's way of reminding us that mystery is baked into the very structure of space itself. That even with all our telescopes, satellites, and theories, we're still learning to see what's actually there. That's what Vera Rubin gave us. Not just a discovery, but a shift in perspective. She looked into the dark and saw that something was missing, and instead of ignoring it, she followed it, quietly, carefully, without the need for attention or drama, just the work, the data, the truth. Today, her name is etched into the night sky. A telescope being built in Chile, one of the most powerful survey instruments ever made, will carry her name, and it will look deeper into the dark than we ever have before. Maybe it'll find the answer, or maybe it'll just uncover more mystery. Either way, the universe keeps spinning, and something invisible, is keeping it all together. The star, older than the universe. In the early 2000s, astronomers stumbled onto something that sounded completely absurd, a star that on paper was older than the universe itself. It was officially named HD 14283, but scientists quickly gave it a more poetic nickname, the Methuselah star, after the biblical figure said to have lived longer than anyone else in recorded history. At first glance, it looked like just another dim star tucked away in our galaxy's halo, the massive spherical shell of ancient stars that orbits the Milky Way. It didn't seem all that special. It wasn't the brightest. It wasn't the largest. It didn't have planets, or weird flares, or exotic radiation. But when scientists started trying to figure out its age, the numbers that came back left them stunned. This one quiet star, barely visible through a backyard telescope, appeared to be roughly 14.5 billion years old. Let that sink in for a second. The universe, based on all our current data from the cosmic microwave background and redshift measurements, is estimated to be around 13.8 billion years old. That number isn't random. It comes from extremely precise observations using satellites like WMAP and Planck, which study the oldest light in the universe. They measure how fast the universe is expanding, and then use physics to rewind the clock back to when everything began. So how in the world could a single star be older than time itself? That's the kind of puzzle that sends scientists spiraling. Not because they love drama, but because the entire foundation of cosmology, how we measure the universe's age, how stars form, how time flows, relies on consistency. If even one piece doesn't fit, the whole structure starts shaking. So naturally, astronomers went back to check their work. Over and over. They looked at the star's light. Light is a star's fingerprint. It tells us everything, what it's made of, how hot it is, how fast it's moving, and crucially, how old it might be. The Methuselah star had a very low metal content, and in astronomy, metals mean anything heavier than helium. Stars born in the early universe were mostly made of hydrogen and helium, because heavier elements didn't exist yet. They're cooked up in stars and spread by supernovae. So if a star has almost no metals, it's a clue that it was born very early, before the universe had time to enrich itself with heavier stuff. HD 140283 had almost no metals. That made sense. It was likely one of the first stars ever formed after the Big Bang. That alone made it interesting, but not unheard of. Astronomers have found other ancient stars like it, relics of the early universe still drifting through our galactic neighborhood. But the weird part came from its life cycle. See, stars age in predictable ways. They burn hydrogen into helium for billions of years, and their brightness and temperature change in known patterns. So by comparing the Methuselah star's color and brightness to models of how stars evolve, scientists can estimate how far along it is in its life, and therefore how long it's been burning. When they plugged in the numbers, the result was 14.5 billion years, give or take a few hundred million. That give or take is important, because science isn't always exact. It works in ranges. At first, the uncertainty was big enough that maybe, just maybe, the star was actually younger than the universe, just barely. But as observations improved and instruments got sharper, the range narrowed. It still floated right at the edge of what should be possible. So what could be going on? One idea is that the stellar evolution models themselves are a little off. When we calculate a star's age, we use simulations of how stars burn their fuel based on physics we've tested on Earth and seen in other stars. But there's a catch. We've never directly observed a star exactly like the Methuselah star at that exact stage of its life. So, it's possible that small details in those models, things like how certain elements behave at extreme pressures, or how efficiently helium is mixed in its core, could be skewing the results. Another possibility lies in the star's distance from Earth. If we think it's farther away than it really is, it would seem dimmer, and we might assume it's older. But newer measurements from the Hubble Space Telescope helped pin that down more accurately, reducing one major source of error. Still, even after refining the distance, the age estimate stayed troublingly high. Then there's the fact that the Methuselah star isn't standing still. It's racing through the galaxy at an incredible speed, much faster than typical stars in our galactic disk. It's a sign that it's part of the Milky Way's ancient halo, likely formed from the debris of smaller galaxies that merged with ours long ago. This also supports the idea that it's incredibly old, but again, that's not enough to explain why it appears to predate the Big Bang, so maybe the issue isn't the star, maybe it's the universe. There's a growing tension in cosmology right now. Two of the main ways we estimate the age of the universe are starting to disagree. One method involves looking at the cosmic microwave background and modeling the early universe's expansion using satellite data. The other method is more direct, measuring how fast nearby galaxies are moving away from us right now, in the present day. This is called the Hubble constant. The problem is, these two measurements don't match. They give different answers for the age of the universe, and the gap isn't shrinking. It's getting more pronounced as the data gets more precise. This disagreement is known as the Hubble tension, and it's one of the hottest debates in astronomy today. So when we say the universe is 13.8 billion years old, we're using one particular interpretation. It's backed by a lot of evidence, but if it turns out to be off by just a few percent, suddenly the Methuselah star isn't impossible anymore. There's also another idea floating around, one that's much more radical. Some physicists think that the way we experience time may not be the full story, that under certain extreme conditions, like at the beginning of the universe, time itself may behave differently. We already know that time is flexible. Einstein's theory of relativity tells us that time moves slower near strong gravity or at high speeds. So, is it possible that our assumptions about time's flow in the early universe are slightly off? Could that shift make room for the Methuselah star's bizarre age? It's not a mainstream idea, but the star keeps the question alive. To be clear, most astronomers don't believe the Methuselah star is actually older than the universe. That would mean everything, literally everything, we think we know about cosmology is wrong. But the fact that it comes so close to breaking the age limit is a big deal. It forces scientists to keep refining their models. It's like a splinter in the brain of modern astrophysics, a small irritant that refuses to be ignored. And it's not the only one. There are other ancient stars. There are galaxies that formed too early. There are signals from space that don't have explanations yet. The Methuselah star is just one of the more personal ones, because we can see it, study it, watch it. It's right there in our own galaxy, whispering that maybe, just maybe, we still don't have it all figured out. That's the strange beauty of science. Sometimes it takes one star to shake your confidence in everything, not because it breaks the rules, but because it doesn't quite fit. And that misfit, quiet, steady, drifting through space, is exactly why we keep looking up, because the universe still holds secrets. And sometimes, they're hiding in plain sight. Galaxies without dark matter. For decades, dark matter has been the quiet glue holding the universe together. We can't see it, we can't touch it, and we don't know what it's made of. But we know it's there. Or at least, we thought we did. The idea of dark matter was never something scientists set out to find. It emerged from a problem, a crack in the math. In the 1970s, astronomer Vera Rubin noticed something strange while studying the rotation of galaxies. The stars on the edges were moving too fast, faster than they should have been, given the amount of visible matter. If gravity was only coming from the stars and gas we could see, those outer stars should have spun off into space like water, flinging off a spinning tire. But they didn't. Something was holding them in. That something became known as dark matter, a mysterious, invisible form of mass that doesn't emit light or interact with ordinary matter, except through gravity. And over time, the case for it grew stronger. Gravitational lensing, where light from distant galaxies bends around invisible mass. Cosmic microwave background measurements, computer simulations of large-scale structure formation. It all seemed to point toward one unavoidable conclusion. Most of the universe is made of something we've never seen. It became one of the pillars of modern cosmology. Galaxies form inside halos of dark matter. Those halos attract gas. Gas collapses into stars. Stars cluster into galaxies. Without dark matter, the universe as we know it wouldn't exist. At least, that's what the models said. But then, something happened that didn't fit. In 2018, a team of astronomers led by Peter van Dokkum made a discovery using the Dragonfly telephoto array, a custom-built telescope designed to spot faint, low-surface brightness galaxies, objects so dim they'd been missed by many previous surveys. What they found was a galaxy called NGC 1052-DF2, and it didn't behave the way it was supposed to. This galaxy looked ghostly, diffuse and spread out like a puff of smoke. But that wasn't the strange part. When they measured the velocities of the star clusters orbiting within it, something unexpected emerged. The stars weren't moving fast. In fact, they were moving so slowly that the galaxy's total mass could be explained entirely by the visible stars. No excess gravity, no missing mass, no dark matter. At first, it seemed like a glitch, an observational error. After all, one galaxy behaving oddly wasn't enough to overturn decades of theory. Maybe the measurement was wrong. Maybe it was distorted by something we hadn't accounted for. But then they found another, NGC 1052-DF4. Same story, same region of space, same eerie transparency. These galaxies weren't just strange, they were breaking the rules. If dark matter is essential for galaxy formation, how do you end up with galaxies that seem to lack it completely? Some astronomers were skeptical. Rightly so. These were delicate measurements dealing with faint objects and distant systems. Could the distance estimates be off? If the galaxies were closer than assumed, their mass would be lower, and the whole anomaly might vanish. Others wondered if tidal interactions, gravitational disturbances caused by neighboring galaxies, had somehow stripped the dark matter away, leaving only the visible stars behind. But even those explanations came with their own complications. For example, if tidal forces tore apart the dark matter, why did the galaxies remain intact? Why hadn't they been torn to shreds themselves? And why were their internal structures still stable? It became a scientific tug-of-war. On one side, models predicted dark matter as essential. On the other, here were these galaxies calmly defying that expectation. No fiery collisions, no violent histories, just galaxies floating peacefully, without their dark matter halos. Further studies tried to confirm or challenge the findings. Some suggested these galaxies might have formed differently, perhaps as byproducts of galactic interactions, like debris clouds that condensed into stars. Others explored the idea that maybe dark matter isn't as uniformly distributed as we assumed. Maybe it clumps differently in certain environments, or maybe, just maybe, our understanding of dark matter itself needs to be revised. And that's where things get interesting, because dark matter, as central as it is to our theories, has never actually been detected directly. We've seen its effects, we've modeled it, we've built particle detectors deep underground to try and catch a glimpse of it, but nothing, no definitive interaction, no signal, no particle, has ever confirmed what it is. So when galaxies appear that don't seem to need it, we're left with a difficult question. Is it possible that some galaxies form without dark matter? Or are we missing something even bigger? Maybe these dark matter-free galaxies are exceptions, cosmic accidents born in rare environments. Or maybe they're hints of an entirely different kind of physics, the kind that doesn't just tweak our models, but rewrites the rules altogether. Some alternative theories, like MOND, modified Newtonian dynamics, have been proposed to explain galactic motion without invoking dark matter at all. MOND suggests that our laws of gravity break down at extremely low accelerations, like those at the edges of galaxies, and that's why the stars appear to move faster. It's a controversial idea, and it hasn't replaced dark matter by any stretch. But discoveries like DF2 and DF4 keep it in the conversation. Still, there's another possibility, one that's quieter and more unsettling. Maybe the universe is more chaotic than we thought. Maybe nature doesn't play by simple rules. Maybe there are many different ways for galaxies to form, some with dark matter, some without, and some in ways we haven't even imagined yet. And maybe, just maybe, our models are only partially right. Like a map that shows the coastline but misses the rivers. It works, until it doesn't. Since those initial discoveries, more ultra-diffuse galaxies have been found, some with apparent dark matter deficits, others with seemingly normal levels. The Dragonfly telescope continues to uncover more of these ghostly galaxies, and with every new detection, the puzzle grows. Some researchers argue we simply don't have enough data yet, that until we have a statistically significant sample, we shouldn't jump to conclusions. But others say the very fact that even a few of these galaxies exist should shake our confidence, because science isn't about clinging to what we believe. It's about listening when the universe disagrees. So what are these galaxies really? Accidents? Anomalies? Cosmic messages in a language we haven't learned to read? Right now, no one knows. But one thing is clear. These galaxies without dark matter, however rare or misunderstood they may be, are forcing us to look again, to rethink not just what we see, but what we expect, to ask whether we've been looking at the universe through the wrong lens, and in a field where the invisible drives everything we see. That's a very big deal. White holes, theoretical ghosts of the cosmos. Black holes are terrifying. They're like cosmic traps, places where gravity becomes so intense that nothing, not even light, can escape. For decades, they've been one of the most fascinating and mysterious objects in astrophysics, and yet, hiding in the same equations that predicted black holes, there's something even stranger, something we've never seen, something that on paper shouldn't even be possible, but also somehow still is. They're called white holes. If you've never heard of them, you're not alone. White holes are like black holes, bizarre, theoretical siblings. They come from the same math, the same solution to Einstein's equations of general relativity that gave us black holes, also gave us white holes. Only flipped. Think of it this way. A black hole is a region in space where matter and energy fall inward. Nothing can escape once it crosses the event horizon, that invisible boundary, not even light. Once you're in, you're gone. No signals, no messages, no return. Time itself seems to stop at the edge. It's a one-way ticket. Now, reverse that. A white hole is a region in space where nothing can enter, but things can come out. It's the mirror image. Instead of pulling things in, it pushes everything out. Not gently either. A white hole would spew radiation and particles, flinging matter into the universe, while refusing to let anything in. It's like a cosmic fountain in reverse, not creating matter, but ejecting it in an unstoppable stream. Sounds impossible, right? And that's the point. By all practical standards, it kind of is. The idea of a white hole isn't something a scientist came up with in a brainstorming session. It fell out of the math. When Carl Schwarzschild solved Einstein's equations in 1916, he discovered a solution that described a region of space with infinite gravitational curvature, the black hole. But those equations, oddly enough, had two sides. Not just a region of no return, but a region of no entrance, a white hole. At first, this was thought to be a strange side effect, a quirk, maybe even a mistake. But mathematically, it held up. Physicists couldn't just ignore it. It was part of the solution, whether they liked it or not. Still, most scientists were skeptical. They had good reasons. While black holes could form from the collapse of giant stars, something we could, at least in theory, understand, white holes had no clear origin. They didn't seem to fit anywhere in our physical reality. How do you create something that only ejects matter, but never absorbs any? What causes that to happen? Why would the universe need such a thing? More importantly, we've never observed one. That's probably the biggest issue. For decades, telescopes have picked up signs of black holes. Through X-rays, gravitational waves, or the way light bends around them. We even took a photo of one in 2019. But no one has ever found a white hole. No radiation bursts, no unexplained ejections of matter, no regions of space refusing entry. And yet, the concept won't go away. Because the more we learn about black holes, the more we realize how incomplete our understanding really is. One of the biggest questions in physics today is, what happens to information inside a black hole? When something falls in, a planet, a star, even just a few particles, where does it go? According to quantum mechanics, information can't be destroyed, but a black hole seems to do exactly that. Everything that crosses the event horizon gets compressed into an unimaginably small point, a singularity, and that's where our physics breaks down. So some scientists have wondered, maybe it doesn't stay there forever. Maybe, just maybe, everything that falls into a black hole eventually comes out the other side, through a white hole. This idea gets weird fast, because it suggests black holes aren't endpoints. They're bridges, cosmic tunnels. The stuff that falls in doesn't vanish. It gets funneled through space and time and comes out somewhere else, in some other form. Now you might be thinking, isn't that just a wormhole? Kind of. In fact, some physicists have suggested that a white hole could be the exit end of a wormhole, with a black hole at the entrance. It's a theoretical structure called an Einstein-Rosen bridge. Matter falls into the black hole, travels through a narrow tunnel in space-time, and then bursts out through the white hole. Boom, cosmic teleportation. But there's a problem with that idea too. Most models say that wormholes, even if they could exist, would collapse instantly. You'd need some kind of exotic matter with negative energy to hold them open, and we've never seen anything like that in nature. So while it's a fun idea, it might just be science fiction. Still, there's another possibility. What if white holes don't form spontaneously, but evolve from black holes over time? Some physicists working on quantum gravity, that's the elusive theory trying to unite general relativity and quantum mechanics, think that the singularity inside a black hole might not be a true endpoint. Instead, the collapse of matter inside the black hole could reach a maximum compression and then bounce outward. Not instantly, but slowly, over time. That bounce could cause the black hole to eventually become a white hole. This could solve the black hole information paradox. It would mean that matter, and the information it carries, isn't lost forever. It just takes a long, long time to get out. Think of it like this. You fall into a black hole. From your perspective, you get crushed, destroyed. But from the universe's perspective, from outside, the black hole is slowly evaporating, decaying, shrinking. Eventually, after countless trillions of years, it could explode outward, and everything it once swallowed comes spilling back into space. That final explosion could look exactly like a white hole. If that's true, white holes aren't just theoretical ghosts. They're real objects. We just haven't waited long enough to see one form. Of course, that's still speculation. We don't have the technology or the time scale to watch a black hole live out its entire life. And white holes, if they exist, might not last long enough to catch. They might vanish instantly, or be hidden behind clouds of energy, or only appear under the strangest, rarest conditions in the universe. But maybe we've already seen one. Some scientists have pointed to mysterious gamma-ray bursts, sudden intense flashes of high-energy light from deep space, as possible white hole events. These bursts last only seconds, but they release more energy than our sun will emit in its entire lifetime. No one knows exactly what causes them. Maybe it's two neutron stars colliding, or maybe it's something else, something impossible. White holes remain a mystery, a mathematical curiosity, a haunting reminder that even our most powerful theories still have shadows. They exist on paper, but not yet in the sky. They could be the key to solving the deepest riddles of space and time, or they could be nature's biggest red herring, a solution without a problem. But the universe has a strange way of surprising us. And if white holes are out there, waiting, hiding, bursting briefly into reality, they could change everything we think we know about black holes, about the birth and death of matter, and about how time itself really works. Until then, they remain on the edge of imagination. Not quite science fiction, not quite science fact, just a question waiting for an answer. Neutron stars that shouldn't exist. They were supposed to be the final act. The remnants of stars that had burned through their lives in spectacular explosions. Supernovae so intense they could outshine entire galaxies for a moment in time. What was left behind was something stranger than anyone could have imagined. A neutron star. These objects aren't just dense. That word doesn't really do them justice. Imagine taking a star larger than the sun, crushing it down until it's no wider than a city, and packing all that mass into that tiny space. A single teaspoon of a neutron star would weigh billions of tons, roughly the weight of a mountain. That's not just mind-bending, that's reality. And for decades, scientists thought they understood them. There was a limit, a boundary line between what counted as a neutron star and what collapsed even further into something darker, denser, and more mysterious, a black hole. That boundary is called the Tolman-Oppenheimer-Volkoff limit, a theoretical ceiling on how much mass a neutron star can support before gravity takes over completely. The idea was simple. Stack too much matter into a neutron star, and it can't hold itself up anymore. The pressure from its own gravity wins, and the object collapses, crossing a threshold where not even light can escape. A black hole is born. But science rarely stays simple for long, because recently, astronomers started spotting something that shouldn't exist. Neutron stars. Too massive to be neutron stars. Objects that were, by every known law of physics, in violation of the rules. It began quietly, with strange readings from pulsars. Pulsars are a kind of neutron star that emit beams of electromagnetic radiation from their poles. If those beams sweep past Earth, we detect them as regular, pulsing signals, like a lighthouse in space. These signals are incredibly precise, allowing astronomers to measure the mass of the star with remarkable accuracy. And some of those masses didn't make sense. Instead of hovering below the safe limit, around 2 solar masses, some neutron stars were coming in heavier, much heavier. One particularly jaw-dropping example was PSRJ 0740 plus 6620, a pulsar in a binary system. Measurements put it at around 2.14 times the mass of our Sun. That was dangerously close to the theoretical breaking point. Others weren't far behind, and one after another, these stellar remnants started piling up, mocking the very limit that was supposed to define them. So what's going on? To understand the confusion, we need to go inside a neutron star. Not literally, but theoretically. When a star collapses into a neutron star, the atoms are crushed so tightly that electrons and protons fuse into neutrons. That's where the name comes from. A star made almost entirely of neutrons. It's essentially a massive atomic nucleus, only held together not by electromagnetic forces, but by pure gravity. Now, neutrons do resist being squeezed together, thanks to something called neutron degeneracy pressure, a quantum mechanical force that keeps them from occupying the same space. That's what props up the neutron star against total collapse. But this resistance has a limit. At some point, the pressure of gravity becomes too much, and neutron degeneracy breaks down. Beyond that, the neutrons themselves are crushed into something else, something even more exotic. The real question is, what happens in that moment, just before the collapse? What happens inside those stars that seem too heavy to exist, yet haven't become black holes? One possibility is that neutron stars aren't made only of neutrons after all. The core of a neutron star might go beyond neutrons and form something called quark matter. If neutrons are crushed hard enough, their own substructure, quarks, could be released into a dense soup of fundamental particles. Instead of a sea of neutrons, you'd have a sea of free-floating quarks, especially up, down, and possibly strange quarks. This would create what physicists call a quark star, an ultra-dense object even more compact than a neutron star, but not yet a black hole. But we've never confirmed a quark star. Not yet. Another theory involves extremely strong magnetic fields, billions of times more powerful than anything we can generate on Earth. These might create a sort of pressure that counteracts gravity, allowing the neutron star to stay intact even when it's over the supposed mass limit. In some cases, these ultramagnetic neutron stars are known as magnetars, and their intense fields could change how matter behaves at those extremes, essentially rewriting the rules of collapse. Yet another idea challenges our very understanding of gravity. Some researchers speculate that what we think of as too massive might not be the same under certain conditions, especially if Einstein's theory of general relativity breaks down at extreme densities. Perhaps at the heart of a neutron star, space-time behaves differently than expected. Maybe gravity isn't uniform across all scales. It sounds radical, but if these massive neutron stars keep showing up, we might have to consider it. Astronomers are now using gravitational wave detectors like LIGO and Virgo to study neutron star mergers. These cataclysmic collisions send ripples through space-time and offer clues about the inner workings of these dense objects. In 2017, when scientists detected gravitational waves from 2 neutron stars crashing into each other, an event called GW170817, they learned something vital. The stars involved were close to the mass limit, yet they didn't immediately form a black hole after the merger. They lingered, just long enough to suggest that ultra-massive neutron stars might not be so impossible after all. In fact, some now think that neutron stars might not have a sharp mass cutoff. Instead, there could be a kind of twilight zone, where certain internal structures or unknown phases of matter allow them to temporarily defy the collapse. If so, the Tolman-Oppenheimer-Volkoff limit isn't a hard wall. It's more like a fuzzy boundary, a place where strange things happen. And if that's true, then maybe these stars aren't breaking the rules. Maybe we just don't fully understand the rules yet. This isn't just a minor footnote in astrophysics. It challenges our understanding of how matter behaves when pushed to its absolute limits. It forces us to think deeper about what's really happening in the universe's most extreme environments. Neutron stars are cosmic laboratories, places we'll never reach physically, but whose properties stretch the very theories we rely on to describe the universe. They reveal the tension between the known and the unknown, between what we believe is possible and what actually happens when the universe decides to surprise us. And so these ultra-massive neutron stars sit out there in the void, spinning silently, defying expectation, reminding us once again that the cosmos is under no obligation to follow the rules we've written down. Monster galaxies in the early universe. When the James Webb Space Telescope finally launched and unfolded its golden mirrors in space, astronomers held their breath. Years of engineering, budget debates, delays, and ambition had finally paid off. The mission was clear: peer back in time, further than we've ever seen before. Back to the first few 100 million years after the Big Bang. No one expected the images it sent back to break the universe, because just weeks after James Webb went live, it did something that threw a wrench into decades of cosmic theory. It saw galaxies, not just smudges of light or baby star clusters. Actual galaxies, massive, bright, mature galaxies that were already formed just a few 100 million years after the Big Bang. That shouldn't be possible. According to the models, galaxies need time to gather gas, time for gravity to pull that gas into clouds, time for stars to ignite, live, explode, and scatter heavier elements, time for those elements to build planets, more stars, and eventually structure. This process is supposed to take billions of years, but the galaxies Webb found looked like they had already been through all of that in just a tiny fraction of that time. They were big. Some rivaled the size of the Milky Way. That alone is shocking. Our galaxy took billions of years to grow into what it is today, and yet here were these cosmic giants, already built, already full of stars, already showing signs of structure like spiral arms or dense central bulges. In a timeline where the universe should have still been foggy and chaotic, these galaxies looked calm, finished, like they had skipped the messy early years entirely. Scientists call them monster galaxies for a reason, because they don't fit. They defy every expectation we've had about how the early universe worked. If you imagine the cosmos as a timeline, these galaxies are showing up long before they're supposed to exist. So how could this happen? How could the early universe be home to such enormous, mature galaxies? The first theory was simple. Maybe we were misreading the data. Estimating the age and size of galaxies based on light alone isn't easy. It involves decoding redshift, how much the light from a galaxy has stretched due to the expansion of space, and comparing that light to models of stellar evolution. Maybe some astronomers thought these galaxies weren't as massive as they appeared. Maybe their redshifts were off. Maybe they weren't really that old. But follow-up observations didn't help. In fact, they made the problem worse. More galaxies kept turning up. Some of them had even redder light, even greater mass, even more structure. This wasn't just a one-off surprise. It was a pattern. And when something shows up repeatedly in science, it can't be brushed off as a mistake. So then came the deeper, more uncomfortable questions. Maybe something about galaxy formation in the early universe was just different. Maybe the first galaxies formed faster than we thought. Some researchers began to wonder if conditions shortly after the Big Bang were somehow more efficient, more hospitable to building stars and galaxies quickly. One possibility was that the gas in the early universe cooled faster than our models predict. Colder gas clumps more easily under gravity, which would speed up the formation of stars. Another idea was that early galaxies were more chaotic and violent, merging constantly to build up mass at a ridiculous pace. Collisions between young galaxies could have triggered bursts of star formation, rapidly growing massive systems in record time. But even those ideas have limits. There's only so much material available in the early universe, and the math doesn't quite add up. Even under the most generous conditions, it's hard to explain how some of these galaxies got so big, so fast. So scientists took it a step further. Maybe dark matter behaved differently back then. After all, dark matter, the invisible stuff that makes up most of the matter in the universe, is a mystery in itself. We know it's there because of how it pulls on galaxies and bends light, but we don't know what it is. And we've always assumed it behaves the same way throughout time. But what if that assumption is wrong? Some researchers proposed that in the early universe, dark matter might have clumped together more efficiently. That would have created stronger gravitational wells for regular matter to fall into, essentially laying down the blueprints for galaxies faster than expected. If dark matter was more active in the early cosmos, maybe it could have seeded these monsters sooner than our models predict. Others turned to physics itself. What if the rules have changed? Or at least, what if the rules we know today didn't fully apply back then? The early universe was hotter, denser, and more extreme than anything we can recreate in labs. Maybe gravity worked a little differently. Maybe fundamental constants, like the speed of light or the strength of gravity, shifted ever so slightly in those early moments, just enough to accelerate structure formation. It sounds wild, but in the face of evidence that breaks your model, every possibility has to be considered. There's also a more radical idea. Maybe the universe isn't as old as we think. If the entire cosmic timeline is off, even just by a little, it could shift our understanding of when these galaxies should have formed. But this would mean revisiting everything: the Big Bang, the cosmic microwave background, the expansion rate, even Hubble's constant. And right now, there's a major debate in cosmology about that very thing, often called the Hubble tension. Different methods of measuring the universe's expansion rate give different answers, and no one's quite sure why. The existence of these early monster galaxies just adds fuel to that fire. In a strange way, these galaxies have become a cosmic mirror. They're reflecting back not just light from the ancient past, but the limitations of our knowledge. They show us how fragile our theories really are, and how quickly they can fall apart under new data. The James Webb Space Telescope was built to look for answers, but instead, it found a new kind of question. A question so big, so foundational, that it forces us to ask if the universe we think we understand is actually something completely different. And maybe that's the most exciting thing about science, that just when we think we're getting close to the truth, the universe throws us something that changes everything. The truth is, the universe doesn't care about our rules. The universe has never asked for our permission to be strange. It doesn't pause to check our equations before unfolding another layer of itself. It simply is, vast, restless, and unbothered by the neat little boxes we keep on our theoretical shelves. Every time we draw a firm boundary between matter and nothingness, between certainty and doubt, the cosmos sends a quiet rebuttal. It whispers through faint radio hiss, blazes across the sky in supernova light curves, or flickers in the frantic spin of a pulsar too heavy to survive. Our textbooks get a little heavier with annotations, our confidence a little lighter. Think about the curveballs we've already caught. A star apparently older than the universe that birthed it. Galaxies speeding through space without the dark matter scaffolding we thought was mandatory. Infant galaxies, fully grown, staring back at us from the dawn of time. The glow of an ancient fireball, still bathing us in microwave whispers. Each of these discoveries arrived like a cosmic prank. Evidence signed in starlight, stamped return to sender, because no one on Earth ordered it. We scramble for explanations, new particles, new forces, new twists on gravity itself, but the universe never waits for our theories to ripen. It just keeps moving. And that's the point. Science isn't a monument to certainty. It's a living conversation with the unknown. Every contradiction is an invitation, every anomaly a doorway. When a measurement refuses to fit, it's not a problem to sweep aside. It's a gift. The Methuselah star challenged our cosmic timeline. The empty dark matter galaxies poked holes in our invisible safety net. The James Webb monsters showed up early to the party we thought wouldn't start for 500 million years. Instead of closing the book, these surprises crack it wider open, urging us to read the next baffling chapter. In that widening gap between expectation and observation lives the real thrill of discovery. The universe keeps saying, "You don't know me yet," and we answer with bigger telescopes, subtler detectors, faster supercomputers, tools built not to prove ourselves right, but to see where we're wrong. Because in those errors, those glorious, embarrassing, world-bending errors, lie the seeds of the next revolution. The story of science is not a march toward a final truth. It's a dance with uncertainty, each step choreographed by questions we haven't even learned to ask. So when we list the most controversial discoveries, stars older than time, galaxies without gravity, an expanding fabric of space stitched with invisible matter, we're not reciting footnotes. We're reciting love letters written by the cosmos to human curiosity. They remind us that reality is bigger, weirder, and more generous than our imaginations. They remind us that humility is the price of admission to the greatest show in existence. And they promise that tomorrow's sky will hold new riddles, already on their way, traveling at the speed of light toward the back of your mind. Maybe that's the best part, the knowledge that we will never run out of mysteries, that certainty is an illusion, and that wonder is renewable. The universe keeps playing hide and seek with its deepest secrets, and we keep counting down, eyes wide, hearts racing, ready to chase after whatever appears next. If you found this journey into the universe's strangest discoveries mind-bending, drop a comment below and share which cosmic mystery fascinates you the most. And if you haven't already, don't forget to like the video and subscribe so you won't miss our next deep dive into the unknown. Thanks for watching, and keep questioning everything, because the universe is far stranger than we can imagine.